This is Group 3's presentation. We had problems 3.12 and 4.3. So, problem 3.12 says, using the method of joints, determine the force at each member of the truss shown. Summarize the results on a force summation diagram and indicate whether each member is in tension or compression. So in order for the truss to be in equilibrium, each of these joints has to be in equilibrium. And in order to evaluate those joints, we first need to find these forces, dy, dx, and ax. So we take the moment around D, and we have ax times 20, which is ax is here, so 10 and 10 is 20, minus 1,000 cosine 30, which is up here, times 10, because that distance is 10, minus 1,000 times 20, which is right here, this force, and then 10 feet here, another 10 feet here. Isolating ax on one side, you get 1,433. So to find dx, you take the sum of all the x forces, just dx plus ax, minus 1,000 sine 30. You substitute the number that we found on the previous slide, 1,433 for ax, and you get dx plus 1,433 minus 1,000 sine 30 equals 0. Isolating dx on one side, you get 933. In order to find dy, you take the sum of all the y forces. So dy minus 1,000 cosine 30, once again, back up here, minus 1,000, which is this force up here. And isolating dy on one side, you get 1,866.02. Now that we have those forces figured, we can isolate the joints one at a time and figure out their equilibriums. So for FCF, which is this segment right here, we have negative FCF. We're going the y forces here. Negative FCF sine 45 minus 1,000. So you have this is the minus 1,000, and you have this 45-degree angle going down. So isolating FCF, you get negative 1,414.21. And because it's negative, that's a compressive segment. So for EF, which is this segment right here, we take the sum of all the x forces. So you have negative EF minus FCF cosine 45 equals 0. You take the FCF, which we found on the previous slide, of negative 1,414.21. And if you isolate for EF on one side, you get 1,000 pounds. And because that's positive, it means that that segment is under tension. So solving for EC, which is right here, we have to take the sum of all the y forces. So negative EC, because it's going down, minus 1,000 cosine 30 equals 0. Isolate FEC on one side, and you get 866.02. And again, because that's positive, it's under compression. So for ED, right here, take the sum of all the x forces. You have negative ED, because it's going in this direction, plus EF, because that's going in this direction, minus 1,000 sine 30. And you get isolating for ED, you get 500 pounds of tension. For the segment AC, take the sum of all the X forces, you get AX plus FAC sine 45, isolating for that AC, you get 2026.57, and it's negative, as you can see up here, so that's compressive. So if we want to find AB, which is right here, we have to take the sum of all the Y forces. If you isolate at A, which would include FAB and FAC, so you have, that should be an F, FAB plus FAC cosine 45 equals 0. We had already found FAC, which was the negative 2026.57 in the previous problem. And when you isolate for AB, you get 1,433 under tension. So for BC, as you can see, that's just 0 because there's no forces on the x-plane. So for BD, right here, we take the sum of all the y forces, and we have BD minus AB, which we found in the previous problem. So you have FBD equals FAB, which just means it's the same as AB, which we already found. So 1,433 of tension. So looking for DC, we have FDE plus DX, which was that outside force acting on it, plus FDC cosine 45 equals 0. We have FDC cosine 45 equals minus 500, which was this dx that we found previously, minus negative 933, which is FDE, which we had found previously as well. Isolating for FDC, we get 612.35, and it's positive, so that's under tension. Here I have a force summation diagram that I put together once you have all those answers, and indicates whether it's under tension or compression. And that is how you solve for the forces in the truss to make sure it's in equilibrium. So question 4.3 is tracing loads. Trace the loads through the following elements in this structure. Occupancy live load is 40 pounds per square foot with a floor dead load of 5 pounds per square foot. And it wants you to trace through the rafters, stud walls, roof beam, columns, floor joist, floor beam, and the load on top of continuous footings, as well as the critical interior footing load, which is this interior footing that the columns sit on. So first, to start with the rafters, you have the snow load, which is given, and the rafters are 24 inches on center, so to make it in feet, you have to divide by 12. So that would effectively be 2. 20 times 2 is 40. The sheathing, roofing, ceiling, and rafters are 3, 5, 2, and 3 respectively. And you have to do the same thing there to get 26. You add those together, and that's a total load of 20 this is the diagram for the problem of the rafters, essentially, to see what kind of load they transfer to the walls. So each wall has a reactionary force going back up because the rafters have a load that goes down and the walls have to support it. So I've assigned this wall R1, this wall R2, this wall R3, and this wall R4. So essentially what this is saying is that the sum of R1 and R2 have to equal the load that's placed on them. So right here you have to take the moment around R1, and the reason you have to do that is because it's not an evenly placed load and we have this overhang right here. So you take the moment around R1 and you do the negative 66, which we found from the rafters, times 12 feet times 6 feet plus R2 times 12. So you get that by referring to the diagram. And so R1 carries half of this load right here because R2 carries the other half. So solving for that, you get R2 equals 396 pounds. After that, you can plug it back into the equation and you get R1 also equals 396 pounds. Plug it back into that equation. So then you have to do the sum of the y forces going that way. And you have 0 equals R3 and R4 minus 66 pounds times 14 feet minus 4 feet times 66 pounds. So taking the moment around R4, you have the 66 times 14 times 7 because it only supports half of this, R3 supports the other half, minus 66 times 4 times 2, which is this section right here, which is 4 feet long. And then you subtract 14 feet times R3, you get R3 equals 424.3 when you isolate that, setting it equal to 0. So you have R3 plus R4 minus 1,188 equals 0, which we found up here. Substituting the 424.3 that you found for R3, and then isolating R4 on the other side, you have 764. And then you have all those reactionary forces, force 1, 2, 3, and 4. I have them down here. So you have 396, 396, 424, and 764. I also have it right here. And it's important that we notice that those are all per 2 feet because those rafters are 2 feet on center. Oh, and also it's important to notice that this reaction at the beam right here is 424 plus 396 because it's supporting half of this and half of this distance. So the load at the base of the front wall is 764, which we found right here, but that's per 2 feet. So per foot, per linear foot, it's 382. And then you add the dead load, or the total load that we found from the rafters, to get 446 pounds per linear foot. At the back wall, which is right here, we have 396 per 2 feet. So you divide that by 2 to get 198 pounds per linear foot, and then you add the same load from the rafters to get 262 linear feet. The load at the roof beam right here is those two numbers added together, and then divided by 2 is 410 linear feet. So for the joists, it gives you the 3 pounds per square foot dead load, that's from the joists themselves, 5 pounds per square foot dead load from the floor, and 40 pounds per square foot live load, and that's the occupancy load. So you add those all together, you get 48, and then times 2 feet to get 96 pounds per joist. You do that because the joists are 2 feet on center. So now you can use this equation right here, which is the load times the length divided by 2 equals the reaction. You have 14 feet here times the 96 that we found up there, divided by 2 equals 672 per 2 feet, and that's for the reaction 4 in the joist. So this distance here, and that's the reaction for the front wall. For reaction 3, we have 14 feet times 96 divided by 2 equals 672 again per 2 feet. And the reason we can use this is because we don't have that overhang like we did for the walls, so it makes it easier. Reaction 2 is 12 feet times 96 divided by 2 is 576 per 2 feet. You're going to add those together for the reaction of the floor beam, which will be right here. For reaction 1, you have 12 feet times 96 divided by 2 is 576 per 2 feet. And that's the reaction at the back wall. Next, we have the footings. So to calculate the footings, you have the reaction at the wall, the rafter load, and the reaction at the joist is the load on the footings. So basically all the things we calculated before, but again, we need to make sure we're in the same units of measurement. So for the front footing, we have 764 per 2 feet would equal 382 is in linear feet. And then the 64, which was the rafter load that we found at the very beginning. And then 672 per 2 feet is the reaction at the joist, which we found right in the previous slide. And that all equals 782 pounds per linear foot. The middle one, which they call the critical footing, we'll do on the next page. And for the back wall, we have 396 per 2 feet, which was the reaction at the wall. Divide by 2 is 198 linear feet, again, plus the same rafter load. And then the 576 per 2 feet from the joist is 288 linear feet, pounds per linear feet. That equals 550. So what they call the critical load is this middle footing, what that's supporting. So if you remember, we have R2 and R3 at 424 and 396. And you have columns that are 12 feet on center. So you have R3 plus R2 equals 820 per 2 feet. So that's those two numbers right there. So you divide that by 2 to get it into linear feet, and then multiply by 12 feet on center, and you get a 4,920 pound load just from the column. And then you need to find the load from this floor beam right here, and you have 1,248 per 2 feet, which we found in the floor beam reaction. Divide that by 2, you get 624 linear feet. Multiply by 6 feet because the footings are 6 feet on center. You get 3,744 linear feet. So you add that with the column load and you get 8,664 linear feet for the critical footing load. And that's all we have. You isolated, or not isolated, but traced the load down through all the parts and gave them what each part is supporting, ending with the 8,664 critical footing load. Thanks.